Okay, good afternoon, everyone. Welcome. Today we are going to discuss exercise 7 exercises. Okay, and yeah, we have a pretty light agenda. Specifically, we are going to solely focus on MapReduce, which I think is a pretty interesting topic. So specifically, I will be dividing MapReduce into two parts. Right? I think this is a much easier way to approach this topic. So I will introduce MapReduce as a computing system, and then I will talk about the computational model it's using. I think separating the computation from the underlying system implementation would be a bit easier to approach. And I will specifically talk about the motivation, why we need this system and design, and with regard to the computation model, we'll go through some example questions you might have in the exam. Okay? All right. Yeah, so first, the reason why MapReduce was invented, was created, was basically that Google had too much data, right? Google crowds billions of web pages and also YouTube videos, petabytes of data, and we can't really have these data on a single file system, right? That's why we need a distributed file system, and in our case, this is HDFS. And in the original implementation, there would be Google file system. Nowadays, Colossus, but yeah. And the reason why we have distributed systems is to leverage the parallelism, right? Because we don't want to read billion web pages from a single machine that will take months. If we were to parallelize this computation, it just take a few hours or so, right? And one thing we need to keep in mind is that we need to have a global view of every single piece of our data, right? So for example, if we want to score all our YouTube videos and I want to analyze, well, how many videos, have more than 1,000 views, right? And in that case, I need to know maybe the first part of my video is stored on this part of the cluster, another is on another node, right? So in this case, we have this for free because the name node of HDFS, if you can recall, that gives us this information. And the piece of data in our terminology would be the replica in HDFS, okay? And the second point, the second motivation where MapReduce really comes in handy is that it really minimizes the data movement, right? We have petabytes of data, and nowadays data movement is the bottleneck in computation, right? Whether it's moving data from off-chip to on-chip or even between machines, this is very costly, right? So we want to maximize data locality as much as possible. In other words, we want to do the computation at the place where the data resides. And in this case, what we need is that we really need a centralized scheduling, meaning that we send the computation to the location of the data. So in this case, we have in MapReduce term, this is the job of the job tracker, right? And what we want is we want to collocate the compute, right? The compute in this case could be a map task or a reduce task. And the piece of data we're computing with is a split. So basically, with each split, we want the computation happening on that split together at the same location where the split resides. Okay. So these are the two principles, design principles of MapReduce as a system. Right? Oops. Sorry. So I think this picture shouldn't be unfamiliar to you guys, right? We've seen this a million times in this course. First, we have a bunch of daemons, right, in this cluster. In this centralized architecture, we have multiple nodes or worker nodes. We have a centralized master nodes, and on each of the components, we have a bunch of daemon software running, right? So on the master node, we have the name node, for HDFS, right? And it really contains all the information we need, right? So the directory where the pieces of data locate, and so on. So this is the piece of daemon, right? It's just a piece of software that's always on, and this locates at the name node, right? And sorry, the master node. And what's collocating with it when we have MapReduce is, no surprise, the job tracker. Right, hopefully it's visible. Yes. Oops. And what it does is that, well, for name nodes, the job is that, well, given the file, it's partition or shard the file to different nodes, right? So for example, in this case, I forgot to mention other daemons running on the components. So in this case, on the worker node, what we have is the so-called data node, right? So this is the daemon running on the worker, and also what's collocating with it is the task tracker. From MapReduce, right? So in this case, it's collocating with the data node so that the task tracker can always launch map task or reduce tasks on that node and working on the local split without network transfer, right? For example, and for name node, what it does is that, well, given a part of file, it partitions the file into pieces, in this case replicas, and then it assigns these replicas, given the policy we've discussed, to different nodes. In this case, maybe this is data node 1, D2, D3, all the way to D6. And it says that, well, the first partition to D3, and maybe this one to D4, right? So this split. And so for job tracker, the job of job tracker is scheduling, right? So what it does is it schedules the map task or reduce tasks to different worker nodes, right? So what it does is that, well, maybe, for example, D3, if I want to do a map task on D3, the best way to do is to collocate the task with the data. So in this case, what it says is that, well, maybe you go to T3 as well, right? So in this case, T3 would be this is T1, T2, all the way to T6, right? So task tracker 3, you are responsible for this piece of replica, and you can schedule map task or reduce task on that piece of data. And this kind of collocation, right, is not always possible, right? So this is a collocation that we mentioned, because if we were to have if we were to have a map task happening on this piece of data, we don't need to move it around. But it can happen that, well, maybe I want to schedule another reduced task on the piece of data D4, but the first try is, of course, then the best way to do it is to handle it by T4 as well, right? So say this is the data node 4, and this is the task tracker 4. Wrong color. But what could happen is that, well, maybe all the slots or all the cores, so the logical cores on that node, on that physical machine, are busy, right? So in this case, maybe T4 is busy. So all the computation slots are occupied already, right? So then what we do is that, well, maybe there are another replica, right? So if you can recall, in HDFS, each replica, each piece of data is replicated 3 times by default, right? So in this case, maybe we will have another replica on D6, so data node 6. And in this case, well, maybe we can schedule this to a different slot, so we don't put it on T4. We say, well, T6, you are responsible now for this task, right? So we can collocate the computation, the map task, or any kind of task on that node as well. But it could still happen that T6 is occupied and busy, right? All the computation slots have been utilized already, so it's also busy. So what we can do is that, well, in this case, we don't have another replica on the cluster, for example. What it does is that, well, maybe T5 is idling, well, it has additional computation resources. Then what it does, well, is that maybe in this case you can do this map task on data node 5, right? So, but this piece of data is not on the local node. So what it does is that this really incurs a network transfer, right? So this is network traffic, meaning that we've got to transfer the green replica to D5 in order to perform the computation, right? And this happens very rare because it's a pretty expensive operation. That's why we want to collocate as much as possible the data with the compute without moving data around. And yeah, that's basically the data replication and task scheduling. So this is the data replication, and this part is the scheduling part. Any questions? Sure.
I was just thinking about, because in the original implementation of MapReduce, the slots that are assigned to that map tasks are assigned to produce tasks that are assigned to, they're separate from each other, right? So is it possible that a map slot and a reduce slot are on the same machine? So there's still data collocation possible for?
Right. So, so if I understood correctly, the question is the mapped and reduce slots are pre-assigned. So assigned ahead of time before the computation happening. And is it still possible to collocate, if this is statically assigned, is it still possible to collocate the computation with the data? Is that correct? Yeah, that's a really great point. So typically, this kind of reassignment wouldn't happen in practice because, as I said, job tracker would have the global view of the computation resources in the whole cluster. So it would be already, maybe there's a probe inside the algorithm, the scheduling algorithm, but pretty much it will decide ahead of time. T5 would have assigned a computation, well, the map slot or reduce slot. But it could happen that, all the slots on this node have been occupied, and yeah, maybe when the resource is very scarce, you have to relocate the data. So because it's very static, you can't, when this slot is idling, you fill it in with another task. This is impossible in MapReduce. Yeah, that's why, yeah, it's not very resource efficient, if that answers your question. Yeah, thanks. Any other questions? Nope. Okay. Moving on. So next we will talk about the MapReduce as a computational model. So what I mean by that is that, so from the paper, so the paper, I mean the mandatory reading of the OSDI 2004 paper from Google, Jeff Ding and Sayan. This is a pretty old paper, but I have to say it's a really interesting read. It really tells you how the engineers were originally thinking about the problem and how they tackle the computation on a large scale. And basically, the conclusion was that, well, for all the analytical queries they were trying to do, they figured that most of the computations can be done in two phases, right? It can be first do a map and do a reduce. And for example, I want to count how many YouTube videos, over 1,000 views, and this could be first done a mapping given the local computation of all the videos, and we map all the videos over 1,000 view with a 1, and then we send this key value pair as a mapping phase, during the reduce phase, we just aggregate the results. So basically what you are saying is that, well, if we were to be able to split this computation in this two-stage phase, then we can massively simplify the computation for our engineers. So the only thing they need to care about is to care about the input and output of these two stages. And all the underlying system implementation is not the engineer's concern, which is pretty smart. And secondly, we have the MapReduce task being massively parallel. And this is very crucial for the divide and conquer paradigm we've talked about many times. And yeah, so this is why we can utilize the cluster as efficiently as possible to perform a large-scale computation. Okay. And next, I will give you a very cliche example. I think everybody online explaining MapReduce will use an example of word count. I find this a pretty bad example because it doesn't represent the kind of computation it typically has, but I think it demonstrates the computational paradigm MapReduce represents. Okay, so first of all, what we have is that given a large file, think of it as a very big file distributed over the cluster. What we first do is to split this file to generate the key value pairs, right? In this case, as introduced in the cluster, maybe we just split it line by line to 3 splits, right? So in this case, what this is a so-called split, right? In the MapReduce term. And this is roughly corresponds to a replica. Oops. On HDFS. And the reason why I say roughly is because, well, the last pair of key value can spill over to another block. And in that case, we might need to go over to another node to retrieve that data back. And having separated the original data to different pieces, what we do is that we feed them into a map task, right? So the map task, well, given this piece of local, hopefully, data, it generates this a set of key value pairs. And in this case, this would be the so-called map task. Okay, this is map task. So given the inputs, we have produced a set of key value pairs. And so this is also a map task, and several map tasks can collocate on a single compute node. Right, so maybe this is data node X, for example. And one thing, let's continue. And then what we have is that we have the shuffling phase, right? So these are different phases, I forgot to mention, right? And they should be separate, like this. And what shuffling does is that, question?
Yeah, I was wondering in split, what are the keys and what are the values?
Right. So in this case, it's a bit ambiguous. So because the keys in this case are the words, right? Because we are trying to count the words, the distinct words, and the values would be empty. So into your map function. So if you have a key value pair, in this case, that would be empty. Another way you can do is that the key could be the line numbers, and the values could be the list of words. But it's pretty flexible in this case. Yeah, it depends on the task you want to perform. Right. Yeah, let's continue. So the shuffling phase is often neglected, but it's pretty important and it's performance critical. What shuffling does is that it performs sorting and grouping of the keys, right? So given the list of key value pairs, it sorts by key. So we have beer, con, deer, river, and we group them by key so that we know which part of the data should go to which reduce task. Okay, and then given a piece of grouped data, we perform the reduce task. So this is what? This is a reduce task. Question?
What do you do if, like the reduce task, corresponds to a split, right?
Right.
What do you do if the split is too big to fit on one machine?
Right, that's true. That's a good question. The question is, so what if this split, right, this piece of data is too big for this reducer to handle? So that could happen. So first of all, this would technically not be a split. As you can see, it could be very large. So in this case, maybe this split is this large, right? It can have thousands of pairs. So one thing you can do is that this is one of the augmentations mentioned in the paper. So it has a bunch of augmentations, one of them being performing the combine task. So what you can do is that you can add a combine function. And what this do is that maybe it reduces the task. So this pre-grouping, so it's a pre-grouping or pre-sorting of this task, reduce this to a smaller set, and then this is fed to the reduced task, subsequent reduced task. Yeah, this is one of the solutions you can do. But if it's just too much and you only have one reducer, there's nothing much you can do actually. It's probably not a good fit for the MapReduce computational model. If everything is aggregated to one key, then it's not a very parallel computation per se, I have to say, at least on the second stage. Yeah, and actually that's a good question. One thing I'd like to mention is that, so the intermediate value, so this kind of intermediate value is stored on disk. Okay, question?
How and where is the sorting and grouping now? We don't even, from the beginning, we don't even know what the intermediate keys will be, right?
Right.
So
That's, yeah, that's a good point. So the question is, we don't even know where the intermediate values are, right? And how we can do this grouping and sorting, where we can do it and where can we do it, right? So yeah, maybe first we should start with this. One thing I'd like to mention is that, yeah, so one question for you guys. Where are the where are the results from the map phase? Where are the results of the map phase stored? So where are the results from everything from here? This is mentioned in the paper, yeah?
Memory and potentially split disk.
Partially correct. Yes, so the computation is definitely done in memory. And then what the map, well, at least the original design was doing is that the results will be stored on disk, on the local disk of every single data node. So in this case, if I were to store the list of cars, rivers, key value pairs, what I want to do is that I will store this data onto the local disk of the data node. Okay, hopefully this looks like a disk. This is stored on disk to persist the results. And then after that, this will, and if you can recall how we sort the results in HBase. How we spill the data to disk. Yeah.
Headless entries.
Exactly. So we're not like doing this write through, meaning that given for every generated pair, we write directly to disk, right? That would be very expensive. What I do is that we use LSLM tree, and in MapReduce, all the key value pairs are guaranteed to stored in ascending order of the key. So once they are stored, they will be handled by SLM tree or some similar data structure and algorithm, so that when they are stored on disk, they will be sorted in increasing order with the key.
But what if we don't know the key? Like, we're not guaranteed that the type of the map key is the same as the type. And so how do we know where we're going to query?
Right. So the question is, we can't guarantee the key used in mapping is the same as the key we use in reduce phase. Is that the question?
Yeah, So it's great that we have an ascending order, but if I don't know what key I'm looking for, I can't use that ascending order.
I see. Right. That's a really good question. So yeah. So typically, what you have is that. So in this case, we are using. We know that the key is the words, right? And then after maybe the mapping phase, so the interface of the mappers has the key value arguments, right? And these could be different from that of the reduce function. But the output, so the output of the map phase, the key value format is exactly the same as the input arguments of the reducing function, meaning that the key value pairs output from the map phase have to match the key value pairs used by the reduce phase. So this part, they could be different, but the output has to be different. So what you are sorting is definitely sorting and grouping the key used by the reduce phase.
I think my question is a bit more like maybe a bit broader than that. So if the function that this MapReduce
Right.
is applying is very complicated distributed, then
Yeah.
the intermediate values, like how can we derive what key to use, what key to be searching for in this? We restrict the functions that compute key should be fairly simple. So we can compute everything.
So is the question about like the type of keys it's using, or the kind of intermediate values they produce?
I guess the type.
The type of
Because
keys,
if I
yeah.
want to find that, intermediate value, then I agree that it should match up between the output of the map and the input of the reduce.
Right.
But
I see.
yeah, no, anyways.
Yeah, I think that's a valid question. So the intermediate, the key can be quite complicated because of the computation that you want to perform. But typically, it has to be comparable. So, for example, in Java, you've got to, for each object, you can implement a comparator type, so that the different object can be compared and ordered. But ultimately, this specific type has to be has to be able to be sorted. Otherwise, it's going to be very complicated to sort, as you said. Yeah. For example, if we have a dictionary as a key, well, without a comparator, then it could be very hard to deal with.
I have one more question, that's all right.
Yeah, sure.
Does MapReduce have some way of kind of verifying whether the combined functions applied to it is commutative and associative? Like,
All right.
does it just like fire off a bunch of inputs at it and test it, or does it just assume like you've given me this, I'm just going to hope that it's associative to whatever?
Right. So the question is there a way, internal way of checking whether the combined function we're applying to the MapReduce framework is associative or not, is valid or not? As far as I know of, no. it's like a protocol. So So yeah, it assumes that the developers would know what they are doing.
It's possible in Scala.
It's possible in Scala.
Like,
Uh-huh.
in functional programming, you can just define the combined function is associativity and commutativity.
That's pretty awesome. I see. Yeah,
I
but
guess it's
yeah,
based on C++, or-
mostly in Java.
yeah.
And yeah, so one of the reasons why, sorry, wait, which programming language? Sorry, you were saying?
In Scala?
Yes.
It's like a functional.
So Scala is a very like amazing language, I have to say, because it's can be used as an object-oriented programming language, but it's also functional. So like functions is also the first-class citizen in Scala. So and it's very versatile, where you can do functional programming, defining associative functions, I think. But in Java, I think it's pretty limited as to what you can do. Yeah. But yeah, that's a great point. I need to look into further. Yeah. But yeah, thanks for bringing it up.
So I have
Yeah.
one more question about storing, like persisting disk.
Yeah.
That wouldn't be efficient if you don't have to persist it on disk. Like,
Mhm.
because you will like ship it to other data nodes. Why bother to persist it on disk, then retrieve it again, and then send it over network?
That's an excellent question. Who knows the answer? Why do we have to persist it on disk?
Because it doesn't necessarily fit into memory.
Exactly, yes. So previously the memory was pretty slow. Was pretty small. You can't really fit all the data to memory. That's one of the reasons, but not the main reason. And actually, that's a really great point. I was trying to make a trick question. So actually, you don't have to. So nowadays, it's being redesigned. So Dremel is the upgraded version, if you like, of MapReduce. If you can recall, last session I talked about how Dremel can outperform MapReduce by a large margin, and the reason for that is primarily because of how Dremel does the shuffling. So Dremel does in-memory shuffling. Hopefully it's not too small. So basically, what Dremel does is that, well, writing to disk is too complicated. It's too time-consuming. So, and it's if you can recall, it has a very good, efficient data model. So that for this data model, the data is very, well, you won't, blow up your data like this, having a piece of input data, and you blow up to a large number of key value pairs, and it can efficiently keep the data in memory and do the shuffling in memory. But yeah, I won't delve into that in detail, but that's one of the parts we left behind in terms of the execution plan I mentioned previously. So indeed, you can do not persist this on disk. And I think for the newer versions of MapReduce, they have optimized this part as well. So I think for newer versions, most likely the intermediate results wouldn't store on disk. But this would be this was the design of the first version. Yeah.
You said they had to be stored on disk?
The initial version had to be stored on disk, but nowadays it's not.
I didn't get why they had to be stored on disk in the initial version.
So previously, so I'm guessing, so they didn't have this reasoning in the paper, but previously, first I'm assuming that the memory is not very sufficient, right? So like nowadays we can have gigabytes of memory on the server, 200 megabytes of memory, gigabytes of memory is not a problem, but previously it was not the case. Secondly, they want to maybe utilize very efficient on-disk data structures like LSM, but it turns out it's not worth it to do that. So it's better to do this in memory instead of persisting intermediate results on disk. Yeah, that's a really question.
So when it stores the intermediate values on disk, it bypasses the Google file system. Like it doesn't interact with it.
That's a really good point. So this is indeed. So the question is whether the intermediate results will be stored in the Google file system or the HDFS underlying distributed file system or not. The question is the answer is not. So that's why storing directly on the local file system is relatively more efficient. Yeah. And one question actually, I have a follow-up question. So in this case, if say this map task failed. So after generating all these key value pairs, and it failed, whatever reasons. And in the master node, somewhere can't send bit reads, and after a few seconds, it still doesn't reply. What do we do? Yes. So we have to restart. Why? It is because, exactly your point, because the data is stored on disk and it's only available through that data node. If that data node is gone, then the intermediate result is no longer available, whether it's stored in memory or on disk. So if this mapping task, so this is getting clustered. So if map task failed, we need re-execution. Failed after completion. And we will see how this can be different from the reduced task. Okay. And so the subsequent question is where the result of the reduced task goes. So after, I don't know, producing these key value pairs, where this final results goes.
Allocated distributed file system.
Exactly.
You want to save that, otherwise you have hours to do that.
That's really, yeah, that's great. That's great. So all the results, so the final results, so will be on the HDFS. Okay, this is a separate file system. So the final result will be stored in HDFS. That's why, so maybe you've tried some practical exercises from the notebook. You can see, every time you want to do the same computation again, you need to delete the original directory on the HDFS instead of the original, your local file system. Okay, and the question then comes, if the reduced task failed, after computing this task, what do we do? So if this reduced task, say, produced bear 2, and then it dies, we can't reach, it doesn't reply to the beacon signals anymore, what do we do?
Just restart on a different thing.
Restart, do you mean we compute this again? Actually, no, because this result is persist on HDFS, and it's not on the local disk. So the result has already, if it's been completed, sorry, actually I've mentioned that. So if the result has been already finished, and once it's finished, it's stored on HDFS. And then once it's in HDFS, we don't need to worry about the failure of this reduced task. That's also one of the reasons why in the paper they claim that MapReduce can tolerate massive worker failures to some extent. So, oops.
Like, you don't aggregate the result before putting into HDFS. You just, you send it to HDFS after each result. How do you know where to send it if it's on distributed machines?
That's a good point. Let me first write on this, and I will come back to that question. So if a reduced task failed after completion, we don't care because it's already on HDFS. And the question is, so for this final results we are computing, right? These are the results. Like, where do we store them, right? Why do we originally? Why are we storing them without aggregating them? So for the first question, it goes to different directories. So although, you are seeing them being like aggregated into like this, but they are in different directories. So in this case, this could be the directory 1, directory 2, and so on. And each partition or each key will have a separate file for it. And you might say, well, I don't want that, right? I want an aggregated result, and potentially I want the result to be sorted, right? Maybe I want to sort the values by frequency, as we have done in the exercise practical questions. Maybe I want to do some aggregated analysis on the final results, right? I don't want to separate directories or files. What do we do? So in this case, one thing I'd like to mention is that the results, the final results, is not sorted. So the ordering is arbitrary. Okay, so this is not sorted. Be very careful. Okay. And the question here is how to get ordered final results. Give you some options.
Can you do
Impossible?
MapReduce once again?
Good point. We chain another MapReduce.
Does that have to be an ordering defined? Like, let your keys are unorderable.
You don't have to, but I want.
Okay.
I want my keys to be nicely ordered. Maybe do some post-processing. Bless you. Oops. Other ways? Single reducer, right? You can sort within a single reducer all the keys if you want. Basically, do a post-processing. So it is possible, right? So it's not impossible. It is possible. You can chain another MapReduce. That's a really great point. So do another sorting. Maybe it's a bit overkill. You can do post-processing, and you can have a single reducer, which is not very scalable, but it's possible.
I don't understand how chaining another MapReduce solves it. Like, we've shown one MapReduce, and it produces disaggregated results.
Yeah.
And we're saying doing one more now, which is aggregated results.
Yes. So basically, you can just emit the key value pairs on whatever keys you want to, compute on or sort on, and then you do the sort using the reduce phase. Question?
Sorry, so here our problem is that the result set is sorted by keys.
Mhm.
We want it to be sorted by values, is that right?
Exactly. Or by some other attributes.
But it is guaranteed that it is sorted by keys.
Uh,
So we sort in the shuffling phase.
Right. So the it's sorted indeed in the shuffling phase, but only for the reduce phase. After reduce phase, this task could finish ahead of this task. You know what I mean? So this result could have been written prior to the bear 2 result. So the keys are not ordered in the final results. Question?
I was wondering, where does the result go? Like, would you just store it on the same node as the reduced task operates?
You mean the final reduced results?
Yeah.
The results will be stored on HDFS directly.
Yeah, but that means it's stored on a data node. But can't you just store it on the same node?
Uh-huh.
Like, you can have the data node, the same node as the task tracker node.
That's that could be that could be an alternative design, but I think one of the reasons why they didn't go with storing the final results on disk is the fear of failure. So if you fail that reduce node, then all the things you've done prior to that reduce phase is in vain. So you need to do it again from the start. So if you were to store it on HDFS, then you don't care if the reduce node fails or not.
But you just replicate it and call it the HDFS file.
Yeah, because that's my results. I want it to be safe. So I will replicate this result 3 times and store it on HDFS. I think, yeah, because typically what would happen, so in this case, it's just a small computation, but what it typically does is, for example, it's across the papers published by all the professors every day, and it's a massive computation, and you don't want to lose that data after the computation, I think. And typically, Google, like 2 decades ago, has millions of machines, and thousands of them fails per day, so it's a must to be safe. Sorry, question? Yeah.
Just for my understanding,
Yeah.
the default result that I would get without doing any of these kind of steps would be really this kind of structure where I have a directory for every single task, and then I would have to do like an extra step to get an aggregated result, right?
That's true, yes. So what you get is that for, each part of computation will have a separate file or directory for that file. And if you want to aggregate the results like this, you need to do an extra step, either by either 3 methods I mentioned here. Yeah. Okay, let me check my checklist. Right, I think that's all I wanted to cover. It's a bit clustered, but basically there are a few things you need to keep in mind. Is like different phases: the map phase, the shuffling phase, the reduce phase, and what shuffling does, where the result is stored, and the ordering of the final result. That's pretty much it, and the failure behavior as well. So I think that's pretty much I want to cover. Question?
Answer is all the 3 except the impossible.
Sorry, again?
The answer to how to get all the formal results, it's like...
Yes, so exactly. So the question is, how do we aggregate the results? You can use either of the 3 methods. And each of them has different trade-offs. But it is possible, it's not impossible. Alrighty. Any questions at this point? Nope. Okay. Moving on. Next, I will just go to the boring part. So we've finished the learning part. Okay. So now I will just introduce some typical questions you might get in the exam. So first question you might have is this kind of problems. So given the implementation of a map function and the reduce function, writing this kind of pseudocode, and you need to tell first what it does, right? What it computes. It's computing the average. It's aggregating, I don't know, counting words, counting YouTube comments or something, and then maybe write some equivalent SQL queries and explain whether this reduce function could be a potential combine function, it's associative or not. So if it's not, maybe provide an alternative way of implementing the combine function. So basically this is given the implementation, oops. You need to come up with what it does. Okay, this is the first type of question you might get. And it should be straightforward to get. And I suggest practicing a few this kind of questions. The second one would be the natural true-false questions about the system concept that I just introduced. So for example, for example, if the map function has to generate the same number of key value pairs or not, is this true or false? Yes. So I think these kind of questions should already be quite a piece of cake for you guys. Just to keep this computational model in mind, and also the system model I just introduced. Okay. So this kind of question shouldn't be a problem. And the second question, which is also very frequent in the exam, is that you're given a description of the task you want to perform, and then you want to give the implementation or the algorithm of that task in terms of this 2-stage pipeline, map and then reduce. Okay, so typically I will give you, I will summarize this into two categories. So the first category would be you want some kind of aggregated single value statistic, right? So you want to have a single value result. So let's write this. What you do is that you just map everything to the same key. Not efficient, but this is the way to do the question, okay? So for example, the largest integer is the first type, right? The average of all integers, again, I want just one number. The easiest way to do that is just to send all the key values to the same reduce function, and then you can do all the kinds of magic you want. Similarly, here, yeah, the number of distinct integers, same stuff. Question?
Yeah, what if that brings me to a previous question?
Uh-huh.
What if that file doesn't fit on the machine and you can't map everything to the same key?
Right. So the question is, what if the intermediate result doesn't even fit on a single machine? It could well happen. The same answer. Either you use combine function or you just change the computational model. So in this case, MapReduce is, I think, one of the first like graph model, computational model you can have. Basically, you have a map stage and reduce stage, but you only have two stages, and most likely you will not find, well, it's not sufficient for all your computation you want to perform. So for example, for this kind of computation, I wouldn't say it's a perfect fit for MapReduce. Later you will learn Spark, which is a much better computational model in terms of computational model to have in terms of the generality. So you can perform a computational DAG of whatever stages you want. And that can handle pretty much all the computation paradigms you have. But for now, you have only two stages, and the kind of computation you can perform is pretty limited. Good question. And the second type is what I call a so multiple. Oops, if I can spell multiple statistics. Multiple value or statistics, aggregated statistics. And here you basically need to do this computation separately, right? So in this case, the task 3 and 4, so the set of integers, distinct integers, then you need the pattern 2. And for 4 as well, you need to do this via the second part. But this is really a tip to crack the exam, but nothing else. Yeah. All right, any questions on the tasks, on the type of questions you might get, just particularly on MapReduce? Nope. So yeah, so this is the kind of solution I mentioned. So for example, this is my solution. It's a bit different from the official answers, but they basically do the same thing. So for example, the largest integer, you just map everything to the same key and you just take the max. Right? It's a very a mock example, but you get the idea. Question?
I was wondering, in the exam, they will let us use Python code. Can we also use Python libraries to do computation more easily?
Right.
I mean, like, I can also write like code to compute the mean. There's functions that will probably be better at doing that.
I see. So the question is, can you use Python functions and libraries to write the pseudocode? Because as you can see, I'm basically cheating, right? Using all kinds of synthetic sugar in Python. So the question is, so the answer is straightforward, because in the exam they won't let you write. They will give you a piece of code, typically written not in Python but in Pythonic way. But they will let you understand what they are writing, but they won't let you write the algorithm. So basically, you will be given a bit more complicated MapReduce algorithms, and to identify what they do, and to probably match with the type of computation you want to perform. So given the description of the task and given a list of implementation, you match the implementation with the descriptions. That's the most possible reasons. And it might change, but I don't see a possibility that they would let you write, because 1,000 students could have 1,000 different ways of writing the same piece of code. So yeah, but typically check it out. And then lastly, I would highly recommend trying out yourself the example the example tasks, the practical command line exercises we provided in the notebook. So we've spent a lot of time making it click and run, and also work on Apple Silicons, and you can really try it out. For example, copy paste the file to the HDFS, and then write using the border template code to write the Java MapReduce executable, and then run it on HDFS, and you can get results and performance, and also get familiar with the kind of syntax as well in the code, and what kind of results they produce, and the performance implications, and so on. So it's pretty nice, and I would highly recommend going through it. But it should, there shouldn't be anything tricky there. So I think from my experience running the largest data sets we've provided, so the this one takes just a few minutes, so it shouldn't be a very large task, because I think this is just 1.7 gigabytes. So give it a try, and it really helps you better understand what I've just told. Okay. Any questions? Alrighty, so that's all I'd like to cover, and I will stick around for any questions from the lectures or from the exercises, and thanks a lot.